Hey everybody. This next lesson here is about the rate of radioactive decay. So how long it takes substances to undergo radioactive decay, and they refer to it as half-life. And so what they do is they um, give you the number that it takes for half of the material to disappear or decay, radioactively decay, transmutate, not disappear, but transmutate into another type of material, right? So if we started with 100% of the material, then after one half-life, you got half of it left. After two half-lives, you got half of that left. And then after three halves, you have half of that left. So it's not half and then it's all gone. It's half of the half each time, right? Half of what's remaining each time, let's say. So that's what it is. It's the average amount of time that it takes for half of its original mass to change into the other form. So mathematically, it's a weird fact or weird thing that this doesn't reach zero ever. Just the way that's just the way exponential decay works is a weird thing. It doesn't really matter, but just thought I'd mention it. So if you started with 100%, then you've got your 0.5 multiplying a bunch of times. Well, if you do 0.5 times itself once, twice, three times, and so on, obviously you end up with a power equation like an exponent, right? And so the way the equation works here is, say, if you had, I don't know how to describe this here. So think of it, if the half-life was 10 minutes, then after 10 minutes, you want that exponent to apply once, right? Well, what makes this equal 1? So that after putting in a time of 10 minutes, you get this happening once, the times 0.5. And so obviously you'd have to have divide by 10 there for that to be a 1, right? And so what you have in here is this, well, this is for one half-life, but in the equation that I'm going to be doing, this is going to be the time of the half-life itself. So the 10 minutes, for example. Okay, so I'm a little bit ahead of myself in how I'm showing this, but you want this exponent, right, to be the number of half-lives. What that says there. It's a little hard to read probably, but it says number of half-lives. And so, for example, here, if you bump this up to 20 minutes, well, obviously that's going to be 2 half-lives, which again, that divide by 10. Let me make that green so you can see that it's like a constant value, right? Put in the 20 minutes, divide by 10 gives you 2 half-lives, and you put in, 30 minutes, then you divide by the 10 that's in the exponent. It's in the equation, right? So that would be your 3 for 3 half-lives. Okay, so you can get the mathematical results. So if we did at this stage here, right, we have how much left? Well, that would be the 0.5 times the 0.5 times the 0.5 gives you 12.5% left, right? Or you could do the 0.5, and you could do to the power of 3, which of course that power of 3 would have come from doing the amount of time divided by the half-life length, half-life time. Okay, so in this example that I did would be the 30 divided by the 10, 10 being the 10 minutes it takes for something to radioactively decay, half of it to decay, I should say. Anyways, hopefully that makes sense. The way this looks here, this is the formula that I showed on the other page, right? So you've got your factor of 0.5, they just have a fraction here. You have your time that has elapsed, t, and then you have t with a little subscript 1/2, meaning the time, the half-life time for the substance. And so if you work backwards here, you can tell it's going to be 16 particles, right? So you get the 16, half of them go away, so you have 8, half of them go away, so you have 4, half of them go away, so you have 2, half of them go away, so you have 1. And, at that point, really this one would be at the end of that exponential decay, where this 1 would then transmutate after another half-life, really, right? But mathematically, they're avoiding that there. It's just at the end of the road there. Anyways, so there's that formula again as an example. I had left the equation out originally, but went ahead with it this time. So the equation for this one, what would the equation be for this one? Well, the starting amount of the substance, instead of being 100%, it can just be the value you're starting with. So you can tell here the y-intercept, if you will, right? The original value would be the 1600. So all this is showing is we're picking that equation, right? If if you haven't seen function notation yet, all this is saying is the number that's left, right? So this is number left or amount left, maybe I should say, because it's not necessarily, but that's why they use n, right? So it's amount left. And then it's after t time, right? So after t long, let's say, as a time interval. Right, so that's function notation. That's just saying the probably how do you want to say this? I'm trying to not use the word function. The quantity you're looking for, how much of it's left, depending on the amount of time that's elapsed. And so they literally describe it as the amount that of the substance is left is a function of how much time, or it depends on the amount of time that has elapsed. Right. So this t right here is this number. It's just you put it into the equation. So if you put a if you put a 12 in, right, you put a 12 in, you get the answer that's corresponding to that. So you put a 12 here, that would show you put a 12 there, showing that you're putting a 12 in here, and so on. Okay. This question, no, it just wants the equation here. So I don't have to worry about specific numbers, but the number we're starting with, the n naught, this is a British way of saying the original value or the starting value. So that's going to be your 16,000. You're going to have your 1/2 factor in here, of course, your 0.5. And then this is going to be t divided by the half-life, right? So t divided by the amount of time that it takes for half to disappear. And we can see that from the graph because right here, the half of 16,000 is 8,000. And so you can tell the half-life is 8. And so the equation for this one would be a 1/8. Okay. So at that point, we could plug in any number we want and get the value that would be left over. So if we put in that 12, our calculation would be the 16,000 times the 0.5 to the power of 12/8. Okay, so write that again so you can see it. Squeeze it in here. 12/8. So you just run the numbers, right? So 12 divided by 8 is 1.5. So we'd have 16,000, 0.5, and bottom corner of the smart board's giving me trouble here. 0.5 and what was it? 1.5? Yeah, 1.5. Squeezing at the edge here. And then so we would do 0.5 to the power of 1.5. 0.5 to the power of 1.5 gives us that weird number, and that number then just has to multiply onto the 16,000, right? Because that's that number there, the 0.35 stuff is this, right? 0.35 dot dot dot. Anyways, that number just multiplies onto the 16,000 at that point. And it leaves us with 5,656.85, and just write that out, 5,656.85. 5,656.85. Dot dot dot. Showing that we could keep more decimals. We would decide, of course, appropriately how many to keep, depending on what number of significant digits we had. But you can certainly see that that number matches this value in there, right? So this example kind of shows you all of those things. This was just, yeah, more information to help you with the idea of all of the values. But I talked about it already. I just didn't reveal the information. All right. So that's the half-life equation. Calculations are done with that. And so, we can do any value we want. And the other complication, sometimes they have different time units, let's say. So 17 days is obviously just going to be straightforward, normal stuff. So you would put in your n, and you're plugging in 17 into it. So that's function notation being shown. It's just a way of keeping track of what you've substituted into the equation. And so we'd have our 17 plugged in and divided by 8. And of course, that would just give you 16,000, 0.5 to whatever number that is, and so on, right? So 17 divided by 8 gives us 2.125. Oh boy. 0.125. Then we could do the 0.5 to the power of that 2.125. And that's going to give you 0.229 dot dot dot, let's just say. So 0.229, yep, 16,000, 0.229. And keep some decimals there, of course, when I do my calculations. And so I can just multiply by the 16,000. We've seen two of the most straightforward example of this, or use of this, when you're just calculating a value by plugging in a number. So 366, what was that? 3668 decimal 0 dot dot dot, right? So 368 decimal 0 was a 1 dot dot dot. And I know it was 1/6, so really we're round 2, but my dot dots there indicate that, you know, I'm saying that there was lots of numbers there, and then I would choose to round appropriately. With further thought afterwards about significant digits, right? But we don't have to dwell on that every single time. So here we go. The only trick, something like this, would be just, you know, get the number of days, right? So times 7, sorry, gives the number of days. So it's 14. I almost said by accident. So times 7, really that's like days per week, obviously, right? And so it gives us 14. And if you look at the units, actually, it's like weeks times days per week. And so the weeks cancel out, you're left with days, right? So, but it's very logical. I don't think we have to worry about that too much. So then it would be just n, the number of, the amount of it left, the number of, sometimes it's number of atoms left, or, you know, number of grams left, right? So yeah, so we're putting our 14, and so we have our 16,000, and our 0.5, 14 over 8, and so I'm just going to say, okay, obviously that one is just as easy to calculate out as before, so I don't need to repeat that one a third time. Hours, you know, we have to convert backwards there. So if you're dividing this by 24, that's 17 out of 24, gives you the number of days, right? So it's 0 point something days, right? So I guess you could look at that one as that's hours divided by hours per day, right? Divided by hours per day. Just to show some links back to things you've seen before. This would be hours, just analyzing units here for fun, but you invert and multiply, right? When you're dividing by a fraction. And so just to see that this division makes sense to do, even based on units. If the hours cancels out, leaving it with days. Anyways, just convert to number of days and calculate it out, right? So this would give you the correct number of a fraction of a day. Plug the number in, you're good to go, right? So with this one, whatever that number was, plug that in there, and so on. Check mark. You can just do that, right? Just as an extension beyond, for B here, it should be, could we use this equation in different ways? Like in this case here, it says determine the number of days. So basically it's saying like t equals, that's the unknown number, and we have this initial amount. So the n0, or initial amount, is still the 16,000. And we're just asking, like, how long will it take? So nt, how long will it take to decay to 7,258 grams? Okay, so they're asking what the time is for that. So let's just fill out the equation. So that the unknown t, so we leave it as a t. And then we plug in everything else. So we have our 0.5 and so on. And we have a t over 7,258, right? And so, oh, and we have this number here. Fill that one in. I guess because I normally would start with the official equation. So I'm going to backtrack and do that because it's always good and required to show this, right? So let's just go with the numbers plugged in. It's a bit of a gray area for this one because it's pretty common to start with the numbers plugged in, but maybe I'll do this, right? 0.5 t over t half-life, you know. So there's your official equation, numbers plugged in, the half-life plugged in for oof, did that wrong. It's 8 for this. Sidetracked with other things. Half-life is 8, right? I think I'm double checking. Yeah. So we've got our half-life plugged in. We've got our initial value plugged in of 16,000. We've got our resulting amount left over. And end result is, of course, we're looking for the value of this, right? So some math steps along the way would be obvious to do still. We're going to try and isolate that t variable, right? So we're going to divide by 16,000. And so the 7258 divided by 16,000 gives us, make sure I got the right stuff there. I do. 0.45360 by 0.45365. So that is equal to the 0.5 and then t over 8. Now, we have two ways of going about this. There's a mathematical method that I will show, or really you're just doing like a guess and check routine, right? So if you don't know the fancier math, then you're really just forced to guess and check, which of course that's not the ideal way to do this. But you'd be doing, I guess you'd start with 0.5 and you'd put it to some number and you'd try to get as close as possible to 0.45365, right? And then realize that, of course, the number you get here, so this is 0.453 dot, 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 or whatever, the number you get here, you then realize that that thing is equal to t over 8, and you just eventually solve for t, right? So that number is there, and then that would give you t equals the final result. And we'll backtrack and do this as if we guessed the perfect number, because I'll get the perfect number using the math process that is correct. Right, so 8 times the number to get what t is. Okay. The mathematical process for this is using logarithms. So using the log button. And so your math teacher, hopefully at some point, you'll see logarithms. Logarithms are the inverse of exponential. And so basically, this is an exponential. And so logarithm kind of undoes the exponential part of it. Okay. So I'll show that. So 45365. I'm going to write out the equation so I can show how this works. So what you do is kind of like in sine and sine inverse and stuff like that. You take log of both sides. Let me just space this out a little bit better. Where's my ungroup? I usually use the hotkey on the keyboard for this. So I'm going to space that out a bit so I can write log in here. So you're just taking log of both sides. And this side spits out a number. This side does something based on logarithm rules, which if you've seen the logarithm rules, you know, but otherwise you're just saying, okay, well, you're learning it now instead of having already learned it and then apply it. But the log rule is that that exponent comes down in front. So that's what you can see is, you know, getting rid of the exponential complication, you know, and just giving you, putting it in terms of an equation you can actually just solve. So this gives us t over 8, and then that log of 0.5 is still there to be done. And then here, the actual log of 0.453, you know, 265 has to happen. So I think this calculator is reverse logic. So I'm going to clear, I'm going to type in my 0.45365 number, and I'm going to, boom, I'm going to do log of it. So I hit the log button. Okay? So that gave me a number of negative 0.343 dot, dot, right? And then we'll carry that number down here. We're not doing anything with it yet. I guess I could do the multiply by 8, but let's save that for later. 0.343 dot, 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 equals t over 8. And then we need to do that log of 0.5 still. So 0.5 log of that, and gives us negative 0.301. I probably should have done more decimals or recorded more numbers, but it'll probably be close enough. So negative 0.3 0, 1. The only thing I'm curious about is if there was a number here that I should have rounded better, but let's just see how it goes. We'll know if we did a good job if it works in this when I put the number in here. So now we just need to solve like normal, right? So we're going to multiply both sides by 8, which is similar to that, right? Multiply both sides by 8 needs to happen to make that happen there. So times by 8, just like on that side. And of course, divide now here by that number, right? So we're going to divide out this negative 301. And so in the end, the number calculation I need to do is I need to do the 8 times the 343 number. So 343, again, hopefully there was decent rounding for the final 3 there, but we're good to the second decimal place at least. Times 8, and then divide by the 0.301. And I just ignored the negatives because they're going to cancel out, right? So 2 negatives make a positive, right? In the end here, and so we end up with 9.116. 9.116, and presumably because I kept at least to the 2 decimal places, my 9.1 is good, right? So 9.12 or 9.1 is questionable there, depending on whether that was rounded right. But basically that means that the answer is this. It's the 9.116. Okay, 116, and this was in terms of days, right? So about 9 days later, there should be 7,258 grams left. And so you could test that, of course, and you could have the number in here. So you do your 0.5, and you'd put in your 9.116 number, divide it by 8, operate, and see what you get. Should have the whole thing, though, by the way. So 16,000 is just a check, basically, right, at this point. So the 9.116 divided by the 8, and then you calculate that all out. So let's do our 9.116 divided by 8. Put that number to the power of 5 to the power of that number, I should say. I'm going to store. Yeah, I think that worked. So I'm going to do 0.5 to the power of memory recall. Yeah, right. That thing there times the 16,000 equals. So it's giving us a number of 7,258. But again, it's slightly rounded, right? Because of possible rounding errors along the way. So 7,262, 7,262. Notice how like the 2 digits are okay, but these ones are, we needed to keep more decimals in order to have better precision to the 4th decimal place. Okay, so that's actually kind of a neat the way that happened. It kind of shows the idea of significant digits and the effect, right? You can only trust, in this case, I felt like I could only trust 2, and sure enough, there's 2 that are matching perfectly, right? So see how this one at least is rounded to a 6, and there's my 6. So my 3rd decimal place as a rounding is good, and then it tapers off after that. So just a nice reminder there about significant digits as well. Primarily you're going to be doing like just more straightforward stuff with just plugging numbers in, but it just feels like, it'd be kind of silly not to show the other important skill to do with this stuff. So I'm going to put that on a separate page later, but I can get it off camera here. So here's another one. Neon 19 has a half-life of 17.22 seconds. The half-life value can be any unit. You just have to then deal with those units, right? So in this case, we're going to convert anything to seconds if necessary. So if this is given as a minute, you write it to 60 seconds, or if it's at half a minute, convert it to 30 seconds. So obviously the given numbers are there. You're given the initial amount is 100 milligrams. The half-life being the 17.2, they did as H equals this time instead of T with a subscript a half, just to confuse you. Thank you very much, authors, right? But anyways, as long as you know the concept, it doesn't matter what the letters are, though, right? That's what I always say with my students. Like, the letters don't matter. It's like the concept and where they should be for the relationship is what you should be focusing on, right? So there's the numbers plugged in, and boom, you just calculate it out. And it would have been, of course, this number divided out first, give that, and then 0.5 to that, giving a value, and then multiplying that value to 100. Right? All right. This one is supposed to kind of show you the idea of like calculating step by step and seeing the relationship as well. So if we had 100 milligrams of this substance and 7% decays during each minute, then you could have the final mass here is like the 93% that's left after the 7% is taken away. So you could write this as 100 take away 0.07 times 100, or you could write it as 93. That would be 100 take away the 7%, or you can just write it as the 93% that's left over. Okay, but we end up with the initial mass for the next minute being that 93, which then gets reduced again and reduced and so on. So it goes like, obviously you could just carry out this table step by step without using the equation. I feel like maybe this one maybe should have been done first, but I kind of like the idea of just showing the equation, showing how it works, and then this kind of shows you like why it's true. And so, or somewhat anyways, I might add a little bit to it. Anyway, so if you graph this thing, it'd be just kind of like that first graph we saw. And then if you look, you'd be like, okay, well, after what, around, less than 10, more than 8, so more than 9 even, so 9 point something, right? So they're approximating the half-life is 9.5 minutes. So that's what the question was, just basically, determine the half-life. And so you're just kind of looking for when it goes to half of the original amount, which you can see here. We start with 100, and then we end up with half, somewhere between 52 and the 48, right? So 9.5. Okay. The actual mathematical equation, that you might have seen this in class, where this 93 is the 0.93 times 100. And so then you think of this as 0.93 times 0.93. So there you have your 0.93 squared, right? 0.93 to the power of 2. And that's after 2 half-lives, right? Well, I should have done this one here, I guess, after 2 half-lives, because this one is the 93 times the 100, sorry, times the 0.93 times another 0.93. But anyways, it's not in terms of decimal 0.05 there. So, like maybe we shouldn't analyze that anyways, right? It would be more actually that I'd have to go to here and have my 0.5 left over, and then that's at my 9.5. And so that would be one application of 0.5. And then the next, after 9.5 more, we'd have another application, and that's where you get that 0.50 squared. So scratch that analysis there, because we're not trying to analyze the equation for each minute, right? So they try and standardize it, right? So you can see like the analysis could be right from minute to minute or day to day or whatever, but they prefer to have it this one number, and so you can compare all substances. So you can just say like, what's the half-life? How long does it take half of it to radioactively decay? So hopefully you find those simple enough, just normal stuff, right? Just write down the given information, just like this kind of thing, and calculate it out. So some applications around for this, there's different isotopes of carbon, so carbon-14 dating. Carbon-14 is an isotope of carbon that the value of it depends on whether the substance is alive or not, and how much carbon-14 is in the atmosphere, and so on. And so basically after something is dead, the carbon-14 decays away at a very known rate, and so you can measure what the percentage of carbon-14 is in something, and work backwards to figure out how old it is, right? Which is absolutely this kind of calculation here, right? How many half-lives was it? Right? So that's a very important calculation. That's why I wanted to introduce you to that mathematical process. There's other isotopes of things that help for that too, like aluminum-26 can be used apparently as well for dating. But yeah, it's just about understanding what half-life means and the calculations to do with it. All right. So As always, I hope that helps and makes sense. It's probably, I hope it's helpful just to see the calculations done in real time and just give you confidence to know that that's what you need to do and you're doing it right when you do it that way. So, all right. So that's it for now for me. I was thinking lately, actually, I jokingly have said, make sure to like and subscribe and so on, because like that's what YouTube videos people say. I was thinking actually it'd be a good idea. The more you like, subscribe, reminder bell, comment on it, the more stuff like that, the more the algorithms notice that someone who's looking for physics help, um, you know, it'll channel it'll feed this channel into people's attention or whatever. The algorithms will notify other people of it. So that'd be a good thing, right? If students around the province or country or world, they're looking for physics help, they might find this channel and get help from all of these lessons that I'm working hard to produce. So yeah, I'm gonna start doing that. I'm gonna start asking you to do that. Just why not, right? It doesn't cost anything. Just like and subscribe and even comment or thumbs up or whatever. And the more that happens, since you're searching for physics stuff because you're a physics student, they'll notice like, ooh, this might be good for other people that are searching for physics stuff, and my channel will start to show up in Google searches. So if you want to help out people around you that are trying to learn physics, just do that. It doesn't cost a thing. All right. Anyways, talk to you next time. See you later.